Hi there, and welcome to your Law of the Lever Lab. Kind of a great opportunity for you to play around with the physics engine, brought to you by FETS in the University of Colorado. You can find a link to that or the activity itself embedded in the content for this lab that is in the news item. I'd like to take a look today. What exactly do I want you to do? I want to walk through an example for you that you can use as a model for as you step through. Essentially, I would like you to complete the 6 challenges. Complete the 6 challenges. Now you can do these by trial and error, that's fine, but what I want you to do is using the law of the lever, which always sounds more impressive, I think, than what it really is. Using the law of the lever, show me your solutions. That is, I want the numbers to indicate where you should place a certain mass. And that is the nature of all of the different challenges, as you'll come to find out. So it's not enough just to complete them. You are evaluated on mostly your use of the law of the lever and why you chose to do what you do. I'm going to walk through an example with you today to illustrate that just a little bit further. I'd like you to submit those to the portfolio, which I trust is working okay for you. Okay, a couple of things to remember. The first thing that will ensure your success on this activity is the law of lever, and that is the effort force multiplied by the distance the effort force is to the fulcrum is equal to the lever force multiplied by the distance the lever force is to the fulcrum. And this is for levers in equilibrium. That is, they are balanced. They're not moving around. Equilibrium. They're not bouncing around. They're not moving. Nobody's teeter-tottering. These are for balanced levers. And that's the name of the game today, is for you to get these levers balanced. And to, using math, decide where you're going to put what mass in order to achieve that. So we're going to take a look at that in the example that I'll do for you in just a moment. And the usage of that. The second thing to remember is that when you're given a mass, let's say we have this scenario here. When you're given a mass, let's say the mass is 5 kilograms, and you're asked for the load force, you have to make the mass into a force. And the way to do that is to use the force due to gravity. And remember, the force due to gravity is mass times little g, which is 9.81 units per meter. And the load force is the force due to gravity acting on that mass. So the load force then is equal to mass times 9.81. If you try to put in the mass directly into the force for the load, you won't get the right answer because mass is not a force. You have to make sure you multiply the mass by 9.81 in order to get the load force. So that is key to your success number 2. Number 1, for levers in equilibrium, there's a law of levers. Number 2, you need to translate the mass into a force by multiplying it by the gravitational field strength in the surface of the Earth, which is little g. Okay, let's take a look at an example here. Here's what you're going to see. You're going to see a lever with a fulcrum. And make sure in the upper right-hand corner there's a little box there that says ruler. Make sure you give that a tick because that's going to give you accurate numbers to measure your distance that the load or the effort force are from the fulcrum. Okay, so let's take a look. We got, let's do this scenario. Let's say we got a situation where we have 5 kilograms located 2 meters away from the fulcrum. And in this particular challenge, you have to put a mass at the 1 meter mark. And what mass do you need to put at the 1 meter mark in order to achieve a balanced lever? Well, how do you do this? Well, I have indicated to you that there are 2 secrets to doing this. And the first one is the formula for the law of the lever. So you write that sucker down because that's your roadmap. That's going to tell you what variables you need to know. So let's list the variables that we know, what we don't know. So this is the load force is equal to the mass times little g. The load force is 5 kilograms multiplied by little g, which is 9.81, gives us 49.05 newtons, and that is the load force. We're going to need the distance the load force is from the fulcrum, and that's given us 2 meters. So already we have, let's change that color out, it's terrible. Already we have the distance the load is from the fulcrum. We have the fulcrum force, sorry, the load force. We also have the distance that the effort force is going to be from the fulcrum, which is 1 meter. In this case, that's a given. Has to be at 1 meter. And we need to figure out what mass do we need to place here in order to achieve equilibrium. That is, in order so that this side of the formula is equal to this side of the formula. Well, we know that Fe is equal to m times g. All right, here's how we do it. Let's plug in our numbers right away here. Let's do Fe, we'll leave it as Fe, multiplied by 1 meter is equal to 49.5 newtons, multiplied by 2 meters, and we're going to get an answer of 98.1 is equal to the effort force, and we just divided out the 1 meter there. But we don't want the force, the effort force, we want the mass. And we know that effort force is equal to weight, or the force due to gravity, which is mg equals 98.1 newtons. And I chose my numbers here to make life a little bit easier for us. We know that little g is is 9.81. It does achieve a negative direction in some scenarios, but on this one, and we're going to rearrange and isolate for m. I rescued my decimal point there. And the mass that we need to place 1 meter away to balance this lever is 10 kilograms. Okay, that's what I want to see for your 6 challenges, numbers indicating what masses should be placed in what locations. I'd like to walk through an example of the simulation itself, the little physics engine. I like physics engines because they're so neat, they work so well. They make me ask the question, are they a true physics engine in that do they model reality accurately? And one question you'll want to ask yourself is friction accommodated for in this physics engine or not? Okay, stay tuned for that demo, and then you're off on your own. Good luck. Submit that as soon as you can to the portfolio. Looking forward to seeing what you had to say. And talk to you later. Okay, so let's take a look at this. Try it out for real using this computer simulation to see if we did our math right, to see if it's really true. First of all, we're going to try an example without the right effort force. So let's put our load force in, and we said our load force is going to be 5 kilograms times 9.81 because the load force is the weight of the object, not the mass. The mass is 5 kilograms. We have to multiply that by 9.81 to get the weight. That is mg. Okay, so our calculation said that if we had to place an effort force at 1 meter on the other side, then the calculations say it has to be 10 kilograms. So before we do that, let's put a different mass there to see if it works. So let's do the 15 kilogram, put it at 1 meter, and you can see that the effort force there exceeds the load force, so that is not going to work. And of course the 20 would be too much. So what about the 5? Well, you can see that for equal forces, 5 times little g, they're equal, but the distances between the load force and the effort force are different from the fulcrum. So the formula for law of levers in equilibrium, they're not equal. It's 5 times little g times 1 on one side of the equation, and then 5 times little g times 2 on the other. So they are not equal. In fact, the load force is greater. So according to our calculations, we had to put a 10 kilogram mass at the 1, and you can see that the law of the lever is true. In order to get this guy to balance out, you have to have 10 kilograms at the 1 meter to balance out the 5 kilograms at the 2 meters. And the law of the lever applies for static levers, that is, in equilibrium, they're not moving.